So we have this question here. So by induction, prove that 9 to the power n plus 1 minus 8n minus 9 is divisible by 64 for all n greater than or equal to 1 there. So meaning that here, the first thing that we're going to do here is we need to show that this statement here is true for n equal to 1 here. So we just put that statement there. So we need to show that. So we have to show that it's true for n equal to 1 like this. So you get this expression that we have here. So that is 9 to the power 1 plus 1 minus 8 multiplied by 1 minus 9. So that will give us 9 to the power 2 minus 8 minus 9. So this will give us 81 minus 17, which will give us 64 like this. Okay, so now this 64 that we have here is divisible by 64 without leaving a remainder there. So therefore we can just say therefore this is true for n equal to 1. Okay, so now if it's true for n equal to 1, we go to the inductive hypothesis. Okay, so on the inductive hypothesis, we make an assumption where we assume that it's true for n equal to k here. So now, showing that it's true for n equals to k here, we're going to get this expression the way it is here. Then we're going to equate it to a number. When we substitute what is n with k, we're going to equate it to a number 64 multiplied by a variable of our choice. So in this case, we're just going to use m there. So here we're saying we're going to have 9 to the power k plus 1 minus 8k minus 9 is equal to 64 m here to represent a variable or to represent a number there. Sorry. Okay, so now here we try to make 9 to the power k the subject here, so we know that if powers are being added, then the base is the same, it's just that the powers are different here. So meaning that here we're simply going to have 9 multiplied by 9 to the power k is equal to, take everything the other side, so we're going to have 64 m plus 8k plus 9 like this. Then we divide both sides by 9, so we're going to have 9 to the power k is simply equal to 64m plus 8k plus 9 and everything divided by 9 like this. Okay, so we go to the next step now. So here we say we need to show that it's also true for n equal to k plus 1. So here, why there's n, we're going to replace it with k plus 1, then we start simplifying. Then while we're going to find 9 to the power k, we're going to substitute with this expression that we have there. So here we're saying we're going to have 9 to the power k plus 1 minus 8 open brackets k plus 1 minus 9 like this here. So here we're just going to start simplifying the expression that we have. So that's basically 9 to the power k plus 2 minus 8k minus 8 minus 9 like this here. So this here will just give us so this is the same as 9 to the power 2 multiplied by 9 to the power k minus 8k minus 17 like this here. So let me just scroll down a bit. Okay, so where there's 9 to the power k, we're going to substitute with this expression that we have here. So now we have 9 to the power 2 open brackets, we make a substitution where there's 9 to the power k, we put this expression here. So we have 64m here plus 8k plus 9 divided by 9 like this, then minus 8k in also minus 17 this side. Okay, so 9 there, it will cancel with 1 on top there, so we're just going to have 9 multiplied by 64 m plus here we're simply going to have 72 k, then 9 times 9 plus 81 minus 8k minus 17 like this here. So here we're going to add and subtract the like terms. So then 72 minus 8k here, we're simply going to get 64k. So meaning that here we have 9 multiplied by 64 m plus 64k, then 81 minus 17, we're going to have 64 there. So you notice that 64 is common on all the terms that we have there, so meaning that we can just factor it out. So we factor out the 64 here, we remain with 9m plus 1 or plus k plus 1 like this here. So now, meaning that k can be any number here and m can be any number, so whatever number we're going to have inside the brackets here, if we multiply it by 64, we're simply going to get a number that is going to be divisible by 64 here. So if this is the case here, so we can just say therefore this is true for n equal to k plus 1. So now if it is true for n equals to k plus 1, then we just conclude to say that this holds under mathematical induction. So say this here holds under mathematical induction. Okay, so this holds under mathematical induction for all n greater than or equal to 1 there. Okay,